Welcome back to this video in Engineering Dynamics, and in this video we're going to solve another problem on the topic of work and energy methods. But for this problem we're actually gonna do the topic on power and efficiency. Okay, so the sample problem for this video is taken from the book of Python and Husalas. Okay, so the problem is a 1000 kilogram automobile accelerates under constant power from 90 kph to 144 kph in a distance of 1/4 kilometers on a straight level test track. So number one, determine the horsepower delivered by the driving wheels to the car. And then number two, calculate the power output of the engine if the efficiency of the drivetrain is 82%. Neglect air and rolling resistance. Okay, um, so we have a car here, a car on a test track. So let's say okay, so it says here that it accelerates under constant power from 90 kph to 144 kph. So this one is velocity, right? So let's say this is 0.1, right? And then this one is 0.2. Okay, so the next thing is let's try to convert this 90 kph to meter per second, so 144 kph. So if you convert this one, we get a 25 meters per second, and then at 0.2 we have 40 meters per second. Okay, so this is V, and then what else? This is S is equal to 0, and then this one is at 0.2 we have S is equal to 1/4 kilometers, so it's 250 meters. Alright, so I think that's good to go. So setting up the equation. So recall that power, this is a straight line, so power is equal to force times velocity. But what is force? So force is actually mass times acceleration, or what is acceleration in terms of velocity and displacement. So it's v dv all over ds, right? So let's substitute this all in here. So we have mv dv all over ds times the velocity term here. So we have v times v, which is v squared. So m v squared dv all over ds. Right, so that's the equation, and we will evaluate this from 0.1 to 0.2. Okay, so what's the mass? It's 1000 kilogram times the velocity. Let's integrate this v squared dv, and then on the denominator we shall also integrate this ds. So the velocity from 0.1 to 0.2 is 25, and then to 40, and then for the distance we have 0 to 250. Okay, so let's continue on. So we have, okay, p is equal to 1000 times, what's the integral of v squared dv? So that is v cube, right? V cube all over 3, evaluating from 25 to 40, and then all over for the denominator is the integral of ds is just s from 0 to 250. Right, so 1000 divided by 3. So let's do this first. Let's solve the numerator. So v cubed, so it's 40 cubed minus the lower limit, which is 25 cubed all over the s, so which is 250 minus 0. Right, so this is kilogram, this is meter per second cube, and then this one is meter. So we should have a unit of newton meter per second or watts. Right, so let's try to solve for the value. So 40 cube, 40 cube minus 25 cube, right, times 1000 divided by 3 divided by 250. So 64,500. All right, it should have a unit of watts. So let's check. Okay, checking the unit, or this one. All right, checking the units. Okay, so what's the units of this? 1000. This is kilograms, and then this one is meter per second, right? The velocity is meter per second. So it's cube, so it's m cube s cube, right? And the denominator is 250 meters. It's in meter, right? So meter cube divided by meter. So what's left is meter squared. So we can further simplify m kilogram. Let's pull out the newton here. So kilogram meter per second squared. All right, that's the newton term. So we have a meter that's left here. So 1 meter term, and then another for the seconds. So if you see, this is newton meter per second, so this is watts. So units, okay. Right, so the power is 64,500 watts times wait. Okay, so the problem says that determine the horsepower delivered by the driving wheels to the car. So it should be in horsepower. So how many watts in horsepower? We have 746 watts. Right, so 64,500 divided by 746, we have 86.46 HP. Right, so this is the HP from the wheels. So recall that in our topic of efficiency, so from the engine, okay, so if we'll try to draw it here, we have an engine, and then it's connected to the transmission, and then to the I think differential here. All right, and then this is the wheels. All right, so this is the wheel. So the 86.46 is the horsepower in this at this point, the wheels. So 86.46 HP. So we have an efficiency here a lot in this drivetrain, which is 82%. 82%. So the question is, what is the power here from the engine? So this is the main power source. So, or let's say this is the input, this is the output power. So P engine is equal to, right, so solving for engine power. Okay, so take note, engine power, this is, I think, maybe from the, I don't know if this is brake horsepower. But anyways, so we have this efficiency is equal to input, no, output all over input. Right, so the input power is the engine, and then this is the wheel. So PE is just simply output, which output is 86.46 HP divided by the efficiency, which is 82%. All right, so 0.82 is equal to right, so 105.4 HP. Right, so you can, if you're confused if what should be in the numerator or in the denominator, this is it. The input power should be greater than the output. So if we check, we have the input power is 105. So because there are losses here in the drivetrains, then it says here that we have 82% efficiency. So what's left here is just 86.46 HP. Right, so let's review the solutions that we have. So this is the problem. We are given velocity and then the distances, and then we are asked to solve for the power from the engine, okay, developed in the engine. So first, let's set up the equations. What we know about the power is it's force times velocity. So what is force? Force, we can derive it from ma. So what is acceleration? We can express it as vdv all over ds. So we substitute this everything in here. So what we get is this. So we have v times v here, so v squared, and then substitute all the initial and final conditions that we have. So what we get is actually the value for the power. Right, so 64,500 watts. So we check the units. So that's the reason why I converted this velocity into meters per second, because I just wanted to be the base units. Right, so if you check the units, we get Newton meter per second, so this is watts, so it's okay. Then we are asked to find the horsepower, not the watts. So we multiply this by its conversion factor, which is 746 watts in 1 HP. So we get 86.46 HP. So this 86.46 is actually the power here available in the wheels. So another question for the problem is to calculate the power output of the engine. So take note, even though it says power output, it refers to the output of the engine. So if the efficiency of the drivetrain is 82%, so meaning, so this is the engine. Actually, this is referring to this system. This is the one that's input power here. So the input power, and then it transmit here through the drivetrain. Then since we have efficiencies, we have losses, then we'll have a reduced available power here. So solving now for the engine power, we use this relationship, the efficiency. So 86.46 divided by the efficiency is equal to 105.4 HP. Alright, so in the next video, I think we shall discuss the next topic on momentum methods, or impulse and momentum methods. Right, so see you in the next video.